In the vast expanse of our solar system, astronomers continue to make groundbreaking discoveries, one of the most intriguing being the detection of interstellar objects, ISOs. On July 1, 2025, a significant milestone was reached when astronomers at NASA's Asteroid Terrestrial Impact Last Alert System, ALERT, identified the third interstellar object to enter our solar system, 3I/Atlas. This event sparked intense excitement among the scientific community, marking the beginning of a new chapter in our understanding of the cosmos. Just days after its detection, an international research team led by Michigan State University, MSU, researchers published the first scientific paper on this enigmatic object, offering fresh insights into its origins and composition. Since its discovery, hundreds of hours have been dedicated to studying the object, which has continued to captivate scientists and skywatchers alike. The team's observations aim to answer fundamental questions about the object's trajectory, its physical and chemical properties, and its place in the grander context of our universe. A glimpse into 3I/Atlas. The name 3I/Atlas refers to the third known interstellar object to pass through our solar system, following the discovery of Oumuamua in 2017 and the more recent comet Borisov in 2019. However, 3I/Atlas presents a unique scientific opportunity, as it is the first ISO to be closely observed by the Transiting Exoplanet Survey Satellite (TESS), a mission designed to detect exoplanets. This unexpected intersection of exoplanet research and interstellar science has provided researchers with invaluable data that may help reveal new information about this object's origins and composition. The early observations of 3I/Atlas showed it to be an active object, actively outgassing materials as it sped through the solar system. Outgassing occurs when a comet or asteroid releases volatile substances from its surface, usually due to the heat from the sun. In the case of 3I/Atlas, the early signs of outgassing raised intriguing questions about the object's composition and whether it could potentially contain biosignatures, molecules associated with life, as some of its outgassed materials resemble substances found on Earth that could be tied to the possibility of life. The role of TESS in studying 3I/Atlas. TESS, designed to study exoplanets by observing the transits of distant worlds as they pass in front of their stars, was not originally intended to study ISOs like 3I/Atlas. However, because of the satellite's wide-field observing capabilities, the object's trajectory crossed the orbital plane of the solar system, allowing TESS to capture crucial images as the object passed through. This is where the collaboration between Adina D. Feinstein and her team at MSU came into play. Feinstein, an assistant professor and NASA Sagan Fellow at MSU's Department of Physics and Astronomy, led the effort to analyze test data that provided an early view of the interstellar object, capturing images from May 2025, months before the official detection in July. By filtering out the light from background stars, Feinstein and her team were able to create clear images of 3I/Atlas, which were then analyzed for any signs of outgassing. What they found was startling. The object had already started releasing a cloud of gas, mostly composed of water vapor, suggesting that it had been actively outgassing for a longer period than initially thought. This early data provided a glimpse into the object's potential chemical composition, which had previously been obscured by the blinding light from stars and the dense cosmic background. The presence of water vapor was not entirely unexpected. However, the fact that the object was releasing gases months before it was detected raised an intriguing possibility. Some of the early analyses suggested that the object had also been expelling other volatile compounds, such as carbon monoxide and carbon dioxide. These are of particular interest to astrobiologists because they are key components of biosignatures, molecules that may indicate the potential for life. While there is no direct evidence of life on 3I/Atlas, the discovery of these gases adds a layer of complexity to the object study, inviting questions about its chemical evolution and its potential to harbor clues about life elsewhere in the universe. The role of international collaboration, the success of this project, owes much to the collaboration between scientists across the world. Feinstein was joined by John W. Noonan, an assistant research professor from the Edmund C. Leach Science Center at Auburn University, and Daryl Z. Seligman, an assistant professor and NSF Astronomy and Astrophysics postdoctoral fellow at MSU. Their collective expertise in analyzing and interpreting the data from TESS and other telescopes was critical in piecing together the puzzle that is 3I/Atlas. This collaboration extended beyond the research team itself, as international observatories and space agencies have contributed their observations and expertise. For instance, the Gemini North Telescope, a collaboration between the United States and several other countries, captured detailed images of the object that have provided essential data about its size, rotation, and tail structure. These global efforts underscore the importance of international partnerships in space research, particularly when studying phenomena that lie beyond the scope of any single nation's resources. Insights into 3I/Atlas composition and origins. The composition of 3I/Atlas has been a primary focus of the research team's efforts. By studying the spectra of the gases being released from the object's tail, scientists can gain insight into the chemical makeup of the object itself. The use of powerful ground-based telescopes, such as those from the Gemini Observatory, alongside space-based observatories like TESS, has enabled scientists to examine the object's surface and atmosphere in unprecedented detail. These observations suggest that 3I/Atlas may be composed of a mixture of rock, metal, and volatile compounds, substances that are commonly found in comets and asteroids within our own solar system. However, the object's interstellar origin presents a new challenge for scientists attempting to understand its makeup. Unlike asteroids and comets that originate within our solar system, interstellar objects like 3I/Atlas travel through vast regions of space and may be subject to different environmental conditions that could influence their composition. The object's surface may have been altered by cosmic radiation and other space phenomena, further complicating the analysis. One of the key questions that remains unanswered is where exactly 3I/Atlas came from. The object's unusual trajectory suggests that it is not from our solar system, but instead has traveled from another star system, possibly from the distant regions of the Milky Way. The object's high velocity as it entered the solar system suggests that it may have been traveling for millions of years, long before it encountered the gravitational pull of the Sun. This opens up the possibility that 3I/Atlas may be a relic of another star system, one that has been traveling through the void of space for eons. The role of the James Webb Space Telescope JWST. While current observations have provided significant data about 3I/Atlas, much remains to be learned. The James Webb Space Telescope JWST, with its sophisticated infrared optics and spectrometers, is poised to take the lead in unveiling even more about the object's composition. JWST is capable of observing in infrared wavelengths, which will allow scientists to peer deeper into the object's surface and determine its chemical makeup with a higher degree of precision. As the object continues to move through the solar system and eventually exits our observational range, JWST's data will be crucial in answering lingering questions about its origins and evolution. Feinstein's statement about the importance of learning from ISOs like 3I/Atlas encapsulates the broader scientific goals of these missions. Learning about other solar systems places humanity into context, she said. The study of interstellar objects like 3I/Atlas could offer valuable clues not only about the origins of our solar system, but also about the broader mechanisms that govern the formation of planets and stars across the universe. Ultimately, studying objects from beyond our solar system also brings us one step closer to answering one of humanity's most profound questions. Are we alone in the universe? Each discovery, whether it's an interstellar object, an exoplanet, or the potential signs of life elsewhere, contributes to our understanding of the cosmos and our place within it. As we continue to explore the mysteries of the universe, the work being done on 3I/Atlas will undoubtedly remain a crucial part of this journey, offering new insights into the building blocks of the universe and the possibility of life beyond Earth.